Myself Punyamurthy from Department of Chemistry, IIT Guwahati. I welcome you all to IIT PAL program. In this class, we will study about the reactions of carboxylic acids. And for our convenient, we will divide the reactions into 4 types. The reactions that involve cleavage of OH bond, So, first we will see the reaction where the cleavage of OH bond, basically acidity of carboxylic acid. Then we will see the reaction of carboxylic acid where the cleavage of COH bond takes place, for example, the formation of anhydride and ester formation. Following that, we will see the reaction of the transformation of carboxylic acid into the corresponding derivatives, for example, a reduction of carboxylic acid to alcohols. At the end, we will see, and the functional group will be intact, but part of the molecule and where the CH bond will be converted into functional group. For example, the reaction in the case of benzoic acid, where the aromatic CH bond can be converted into nitrobenzene and so on. For example, in the case of benzoic acid, and the CH bond can be converted into nitro group, and then we will end up with nitrobenzoic acid. Cleavage of OH bond. Carboxylic acid acidic in nature, they can give proton and make salt with bases. For example, when you take the carboxylic acid, react with base, for example, sodium hydroxide, it can form sodium carboxylate and water as byproduct. So, this is a base, this is acid. That acid can, due to the acidic nature of carboxylic acid, it can give the proton, can form salt, sodium carboxylate, and where you generate water as a byproduct. And it can also react with weak base like sodium bicarbonate to give the corresponding carboxylate. And water and carbon dioxide. This is a test we use in the laboratory to find out and whether the compound that we have is carboxylic acid or not. And if you treat with sodium bicarbonate, and you can see the formation, you can see the evaluation of carbon dioxide, then you can tell that the compound has carboxylic acid functional group. This is one of the tests we use in the laboratory to find out the carboxylic acid functional group in organic compounds. And this is when you react with the base and you can make salt. Carboxylic acid also can react with the electropositive elements, metals like sodium can, for example, it can react with sodium, can form again sodium carboxylate, hydrogen gas. So, now let us see the acidity of carboxylic acids. Carboxylic acids are weak acids, and when you take an aqueous medium, they can undergo dissociation to carboxylate ion plus hydronium ion. So, partially they can undergo dissociation, they exist in equilibrium. Both you can find the undissociated carboxylic acid in water as well as the dissociated carboxylate ion and hydronium ion. They exist in equilibrium. This depends upon the strength of the acid. It is not like mineral acid like HCl, which can undergo complete ionization in to Cl minus and H plus. But in this case, since it is weak acid, partially it can undergo dissociation to give the carboxylate anion and hydronium ion. This depends upon the strength of the acid. If the acid is stronger acid, it can undergo dissociation more and you can form the corresponding carboxylate ion. If it is weak acid, partially it can the concentration of this will be carboxylate ion will be less comparing to the undissociated carboxylic acid. So, this can be described the extent of dissociation of the carboxylic acid in aqueous medium can be described using this equation. This is the acid Ka equal to acid dissociation constant. So, the concentration of dissociated carboxylate and carboxylate anion and carboxylate ion and hydronium ion in water in moles per liter divided by the concentration of the undissociated carboxylic acid. This is called acid dissociation constant, and if the acid is stronger, then we have higher integer value, and for our convenient we always express the strength of the acid as pKa equal to log Ka. The strength of the acid can be explained using this pKa value, and this is a integer value, and if the pKa is less, the acid is stronger, and pKa is more, that acid is weaker. This you can see, this is always, if you see the textbook, they write pKa of this acid and carboxylic acid, and the stronger acid always will have less pKa comparing to the weaker acids. And why carboxylic acid is acidic? Why this? This can be explained by the resonance of carboxylate ion. If you take the formic acid for example, the bond length is different. This is shorter, this is longer, the bond length. When you make the corresponding carboxylate ion, This is a resonance structure of the carboxylate ion. This can be drawn like this. If you see, the bond length of this one is 1.27 Armstrong. So, now the bond length is same in both cases. So, this because of the resonance this carboxylate ion stabilized, that leads that makes the carboxylic acid acidic in nature. And the stabilization of the carboxylate anion can be explained by the delocalized bimolecular orbital of the carboxylate anion as this is sp2 hybridized carbon, and now you have unutilized p orbital, and this unutilized p orbital of this oxygen and overlaps with this p orbital of this carbon and p orbital of this oxygen, and make delocalized bimolecular orbital, as you can see here. Like this. This is the delocalized bimolecular orbital. And you look at it, you have 2 electron lone pair. This p orbital has a lone pair, and you have 1 electron, and you have the 3 atoms, 4 electrons. They delocalized and above and below the plane, and make this carboxylate anion is more stable. This is the responsible for making the carboxylic acid acidic in nature, and this is because of this stability of the carboxylate via resonance. Now, let us look at the effect of substituent in the carbon atom. For example, if you have electron withdrawing group, the carbon atom. So, this carboxylate anion is, has electron withdrawing group. The acidity of carboxylic acid increases, because it takes electron from the carbon atom, it makes more acidic, it can easily give the proton. On the other hand, if you have electron donating group on the carbon atom, it can reduce the acidity of the carboxylate. So, for example, let us take formic acid. This unsubstituted carboxylic acid, when you introduce a methyl group, so to the carbon atom, this is a methyl group, as you know, this is a electron donating group. It can give electron to the carboxylate. So, this comparing this is more acidic comparing to this, because if you look at the acidity constant of this will be more acidic comparing to that. When you introduce electron with donating group, the acidity of the carboxylic acid is decreased. And when you go for further, this will be again less acidic, and because the ethyl group can give more electron towards to the carboxylic functional group, make less acidic in nature. And this is the acidity order of when you have the alkyl group, and when you have the, in the case of aliphatic carboxylic acids, and when you have the electron donating group, and so like this and the acidity this unsubstituted the formic acid is more this is called methanoic acid, right, IUPAC name. This is more acidic comparing to the ethanoic acid, and ethanoic acid is more acidic comparing to the propanoic acid. And this is on the other hand, now if let us look at the acidity of this compare the acidity of ethanoic acid this carboxylic acid. So, one of the CH bond can be replaced by Cl bond, and one of the hydrogen has been replaced by Cl. So, chlorine is, as you know, is a electron withdrawing group. Now, the acidity of this is increased. This is more acidic comparing to this, because when you have the electron withdrawing group. When you have the electron withdrawing group, the acidity increases. And for example, if you replace 2 hydrogen atoms, you get the Cl2CH. This is more acidic. And if you introduce another hydrogen, replace with chlorine, you get this most acidic. Among these 4 compounds, the acidity is this more acidic, see again this most acidic. So, when you have introduced electron withdrawing group, therefore, the acidity of the carboxylic acid increases, and similarly, when you introduce an electron donating group, the acidity of carboxylic acid decreases. This acidity of carboxylic acid, when you introduce different substituents, they affect the acidity of carboxylic functional group. Now, let us look at the cleavage of the reactions that involve the cleavage of COH bond. When you have heat carboxylic acid, for example, ethanoic acid with acid like P2O5, it can readily undergo dehydration to give anhydride. These 2 molecules of ethanoic acid combine together to form the anhydride, and water has been removed by the phosphorus pentoxide. So, the removal of water from this reaction by heating using phosphorus pentoxide can produce the anhydride. This water the OH group. The C carbon OH group has been cleaved. This you make here CO and bond, and you make anhydride. This is one of the very important reaction, because we use anhydride as precursor for oscillation reactions, and when you have the carboxylic acid with treat with the phosphorus pentoxide, you can make anhydride. Basically, it removes this water molecule. Phosphorus pentoxide remove the water molecule, and you make anhydride. And also, you can treat with acid. It can also, when you heat the carboxylic acid with acid, it can undergo dehydration to give anhydride. This there are so many methods available. This is one of the method that we use to make anhydrides from carboxylic acid. The second reaction is esterification. And if you have carboxylic acid, for example, ethanoic acid, you can react with alcohol, for example, methanol. The presence of acid or base. It is a reversible reaction. For example, if you treat with acid, they can undergo reaction to give methyl acetate, this ester. You take carboxylic acid and alcohol, they can react in the presence of acid under heating to give ester. This is called methyl acetate, and you produce water, and this can exist in equilibrium reaction. Therefore, whenever we do the esterification, we have to take one of the, this is called Fischer esterification. You take one of the reactant excess and as a solvent, and then you can push the reaction forward to get a sufficient yield, or if you want to make good yield, then you have to remove this water from the reaction mixture by isotropic distillation and so on. Here also, for example, you should not have the water. The water is removed by using the phosphorus pentoxide. If you have water, then it will go back to the reaction. You have to remove, if you remove the water, then you can get good yield of the ester. This is also a very useful reaction to make ester, because and acid can be readily converted to ester, then we can do several organic transformations. Now, let us see the mechanism of this reaction. Protonation of the carboxylic acid can form this intermediate. Once you have the protonated carboxylic acid, this can undergo addition reaction with one-to addition reaction with alcohol can form this tetrahedral intermediate. So, proton transfer form this intermediate. Form this intermediate. Once you form this this proton transfer, if you remember the first part of the carboxylic acid, we studied the mechanism of how you can ester can be cleaved into carboxylic acid and alcohol, the same mechanism here. And this you have the water can remove this proton and you make the hydronium ion. That hydronium ion again can react with this OH, you can give this intermediate. It's basically proton transfer takes place. First remove this proton, and by using water as base you make the hydronium ion. That hydronium ion again can react, and you can make this intermediate. This intermediate can transform into the ester this can be further converted into the protonated ester can be transformed to the ester. So, this is the mechanism how the acid reacts with alcohol, the presence of acid to give ester, and this an equilibrium reaction. The third example is the transformation of acid to acid chloride. For example, this propanoic acid, when you react with phosphorus pentachloride or thionyl chloride, it can be converted into So, the acid chloride, that OH bond, that carbon OH bond undergoes converted into carbon Cl bond. See, this also very important precursors we use as precursor for oscillation reactions. The acid can be converted to the corresponding acid chloride. Once you form the acid chloride, this is more reactive, more electrophilic in nature now compared to the carboxylic acid. Now, we can add nucleophile and we can and easily the reaction can be carried out. And the advantage of this reaction, there are so many methods available, and so one of the efficient method to make acid to acid chloride is to reaction with thionyl chloride, and where you generate sulfur dioxide and HCl as gas, they can go and you will end up with a pure product that will be easier to get pure acid chloride. The third example is the reaction of carboxylic acid with ammonia to produce amides. For example, take benzoic acid. When you react benzoic acid with ammonia, when you pass, it can first it can form the salt. Any carboxylic acid, when you react with ammonia, it forms the salt. Once you form the salt, and when you heat the salt, it can convert into amide. It is also a very useful reaction. And if you have carboxylic acid and ammonia and you can make the salt, when you heat the salt, it can give the amide. In the case of benzamide, you will get. But if you use the aliphatic carboxylic acid, you will get the corresponding amide. And you can also use, in case of if you use the dicarboxylic acid, for example. So, when you react with 2 equivalent of ammonia, then you make the corresponding ammonium salt. This when you heat, you get amide. So, this can be further converted into imide. This is called imide. This is called thalamide. And you can see first you can form the salt. When you heat the salt, you get the amide that can be further converted into imide, and where you by removing 1 molecule of ammonia. So far we have seen 4 examples on the cleavage of COH bond in carboxylic acid, and first we have seen the formation of anhydride. When you react the presence of dehydrating agent like phosphorus pentoxide, and acid can be converted into anhydride. And then we have seen the esterification reaction of carboxylic acid with alcohol, the presence of acid or base, they can be converted into the corresponding ester. The third example, we have seen acid can be readily converted into the corresponding chloride, acid chloride, using reagent like phosphorus pentachloride, PCl3 or thionyl chloride or oxalate chloride. These are the common reagents used to convert carboxylic acid to the corresponding acid chloride. Then the acid chloride is the carbon of acid chloride is more electrophilic in nature. They can readily undergo now addition reaction with nucleophiles at moderate conditions to get selectively the addition product. Then we have seen an example for how you can convert carboxylic acid into the corresponding amide, and first when you add ammonia, then they form salt. That salt, when you heat it, converts into the corresponding amide by removal of water molecule. The next reaction is the reaction of COH group. So, we are going to look at two reactions, two type of reactions. First one is a reduction of carboxylic acid. For example, here the propanoic acid, it can be readily converted into the corresponding alcohol. This is called reduction reaction, and the carboxylic acid is reduced to the alcohol in this case. And the common reagent we use for reduction of lithium aluminum hydride or diborane based reagents. They can readily reduce the carboxylic acid to the alcohol, and of course, you have to during the reaction you have to form the salt, which can do the workup. When you react with water, then you can get the alcohol. So, this very one of the important reaction, how do you convert the alcohol to acid to alcohol. But you cannot use other reducing agent like sodium borohydride, they do not reduce. Of course, sodium borohydride you have to use like iodine recently found that can reduce, but lithium aluminum hydride is commonly used to reduce carboxylic acid into alcohol. This reaction usually carried out in THF. You reflex and you make the aluminum alkoxide. That aluminum alkoxide, when you do the workup, and you can get alcohol. It is a very useful reaction, and we often use functionalized or any carboxylic acid can be selectively reduced. For example, in the case of amino alcohol, you can reduce the carboxylic acid to the amino alcohols. The next example is decarboxylation reaction. When you have the carboxylic acid, when you treat this carboxylic acid with base, and you can convert to the corresponding carboxylate or simple carboxylic acid also when you react with soda lime. So, it undergoes decarboxylation. In this case, you will get if you use ethanoic acid, you will get methane, and if you use benzoic acid, under this condition it will be converted into benzene and sodium carbonate. So, any carboxylic acid when you treat with soda lime a heat, they can undergo decarboxylation to give the corresponding. This is called decarboxylation reaction. The fourth type of reactions is reaction that involves CH bond. For example, when you take this in these reactions, the carboxylic acid functional group is intact, and this part of the CH bond, part of the molecule undergoes reaction, and we will see two examples. One is Hell-Wohlhard-Zelinsky reaction, where, for example, if you have carboxylic acid that contains alpha hydrogen atom. So, this carboxylic acid, when you react with chlorine or bromine in the presence of red phosphorus, it can be halogen and red phosphorus followed by hydrolysis, and the X can be Cl or Br. It can be selectively at the alpha carbon can be halogenated to the corresponding carboxylic acid. For example, if you Br, then you can get alpha bromo propanoic acid. This very useful compound. This compound and can be further converted into a variety of molecules. It basically is a building block. For example, this compound, for example, let us consider this as so 2-bromopropanoic acid. This we can further react with, for example, sodium cyanide. You can do cyanation this, of course, you can do hydrolysis, you can get the dicarboxylic acid. And similarly, when you react with NH2 minus, you can make amino acid, alpha amino acid. If you react with OH minus, you get lactic acid derivatives. So, lactic acid you can form. So, this is very useful reaction, and this alpha halo this carboxylic acid can be converted into different organic compounds by nucleophilic substitution reaction. This is a substitution, this is a nucleophile, and easily can react. This is a very reactive one, and you can convert it into cyano carboxylic acid or hydroxycarboxylic acid or amino carboxylic amino acid, alpha amino acid, lactic acid, and cyanocarboxylic acid, and so on. The other example is functionalization of carboxylic acid. And for example, aromatic carboxylic acid. For example, when you react this benzoic acid with the nitro group, you can form nitrobenzoic acid. You can get nitrobenzoic acid. And similarly, when you react with the cyano group, you can get cyanobenzoic acid. Always this in this case the electrophile undergoes reaction at the meta position carbon number this carbon atom, not here. This can be explained by the if you write the reaction pathway, why selectively the N mode to the electrophile undergoes substitution at the meta carbon atom, not at the para or ortho carbon atom. And this can be explained because this carboxylic acid is electron withdrawing group. And because of this, always the electrophile undergoes reaction at a substitution reaction the meta carbon atom, not para one. On the other hand, if you have electron donating group, and of course, this the reaction will take place para position. This can be explained by writing the resonance structure of this reaction. This electron withdrawing group. So, when you add the electrophile, suppose the electrophile takes place at the meta position, you will have this sigma complex, you will have it. So, if you write a resonance form of this sigma complex, you can the another structure is this can transform into product. If you look at this resonance structures, this benzene ring attacks this nitro electrophile, and first you form this intermediate sigma complex. This complex can be written different resonance forms. If you read the resonance structure of these intermediates and always look at it, this carbocation is present at ortho position, you can see here, and or para position. So, the electron, when you have the electron withdrawing group, and if it undergoes electrophilic, if you add the, if you see, and this carbocation present ortho position, already this is the electron withdrawing group, and this is the if you see add the nitro group, and so this is the these two carbons have less electron density, otherwise the electron deficient, and this is favored, and so this the meta substitution favored. On the other hand, if you write the para substitution resonance structures, on the other hand, if it undergoes reaction here, and if you write the corresponding resonance structure, so it can transform into the product. If you see the resonance structure of okay, this if you compare the resonance structure, if the electrophile undergoes reaction at meta position, you see we will have these three resonance structures. On the other hand, if the electrophile undergoes reaction at para position, we will have these three resonance structures. If you compare these structures here, and this is electron withdrawing group. If you write this resonance structures, we again the carbocation comes this carbon. This is electron deficient, and again is electron deficient. This is very less favorable this reaction pathway. On the other hand, if you write if it undergoes at meta position, and always you can look at it, and this carbon is more electron rich, and comparing to that, therefore, this reaction pathway is favored compared to this. This is the reason why when you have the electron withdrawing group, the electrophilic substitution takes place at meta position, not para position. This can be understood using these resonance structures. Let me summarize. Today we have seen the part 2, the chemical reaction of carboxylic acids, and first we have seen the reaction that involve the cleavage of OH bond, and where we have seen the acidity constant, and we have seen some of the reactions, and what will happen if you react, why carboxylic acid is acidic. This we have seen. This is because when you form the carboxylate anion, that can be stabilized. That stabilization comes from the delocalization of bimolecular orbital between these two oxygen atoms and the carboxylate carbon, and because of that the carboxylic acid is acidic in nature. They can give proton and make carboxylate anion, and the acidity constant is measured using pKa value. The pKa value less means is more acidic. pKa equal to log minus log Ka. Ka is the acid dissociation constant, and the carboxylic acid weak acids, and they are partially dissociated in aqueous medium. And we have seen some of the example. Therefore, when you react acid with base like sodium hydroxide, they can react, form sodium carboxylate, and water is a byproduct. You can also react with a weak base like sodium bicarbonate, where you evolve hydrogen carbon dioxide, which we use in the laboratory to identify whether the compound is carboxylic acid or not. As soon as you add, if it is carboxylic acid, it can evolve carbon dioxide. And then we have seen some of the reactions where you can cleave the carbon OH bond. Examples are the formation of anhydride. If you have the carboxylic acid, when you react with the dehydrating agent like phosphorus pentoxide, it can dehydrate, you can make anhydride, which is also very important precursor in organic synthesis for various oscillation reactions. Then we have seen esterification, and where we can do both acid and base based esterification reactions, and then we have seen how you can convert the carboxylic acid into acid chloride, then we can make it more electrophilic in nature, and this reaction can be carried out using phosphorus pentachloride or thionyl chloride. Then we have seen and the transformation of carboxylic acid to amide, and this can be done by reacting with ammonia. You make ammonium salt. When you heat the ammonium salt, it can undergo dehydration to give amide. And we have seen one example how you can use this method to convert the 1,2-benzene dicarboxylic acid to the tholimide. Then we have seen the reaction where you can convert carboxylic acid into alcohol using reducing agent like lithium aluminum hydride or diborane. You can convert quite efficiently reduce alcohol carboxylic acid to alcohols. And then we have seen decarboxylation reaction. When you have carboxylic acid or sodium carboxylate, when we treat with soda lime under heating, it can decarboxylate to give alkanes. For example, if you take for example benzoic acid, when you treat with soda lime, you can get benzene. At that end, we have seen two types of reactions where the first example involves alba halogenation of carboxylic acid, and when we react, if your carboxylic acid alba hydrogen atom, when we react that carboxylic acid with red phosphorus, halogen like bromine chlorine in the presence of red phosphorus, it can undergo alba halogenation, bromination, chlorination, which can be further converted into different derivatives with the different nucleophiles. For example, we have seen how you can replace the Br functional group using cyano or OH or amino functional group. You can end up with very useful compounds. Then we have seen aromatic nitration, where if you take benzoic acid and why this nitro group selectively undergoes reaction that meta position, not para position, and is because this carboxylic acid is known as meta directing group, and this can be explained by the writing the resonance structures. If the reaction takes place at meta position, we can have this kind of resonance structures, and you can see here, and these are more powerful comparing to that, where if you write if it undergoes reaction at para position, and what happens, you will generate an intermediate carbocation which involves this already is an electron withdrawing group, and again you will generate carbocation. This is not favored, therefore, this is the reason always, and when you do the electrophilic substitution, when your benzene ring has electron withdrawing group, selectively the reaction takes place at the meta position. Similarly, there are many reactions are known, and when you have the benzene ring carboxylic acid, it can be converted into variety of substituted benzene carboxylic acids with a different electrophile. This is one of the example. With this I conclude. Thank you very much.